Abrar Ashraf from Brazil for the presentation. Dr. Abrar Ashraf.
Hi, can you listen me?
Yes, please share your.
Uh, okay, my screen is visible.
Yes, please continue.
Hi everyone, I am Abrar Ashraf. I am from Department of Material Engineering, University of Sao Paulo, Brazil. I am working on high entropy alloys, but today I will also talk about the uncertainty if we analyze the data, how we can detect the uncertainty and we can apply the Neutrosophic statics. So first I will talk about little high entropy alloys and importance of high entropy alloys. And in our data is uncertainty, how we can detect this one. And then we apply Neutrosophic statics. And then I also compare the how this statistical is better as compared to the traditional. First, I will talk about the high entropy alloys. The high entropy alloys concept first time is introduced by two scientists that they published same article in same year. The Genway and Brain Counter is from Taiwan and UK. He discovered the phenomena of high entropy alloys. Actually, the high entropy alloys we can say, for example, if I have more than five element, I combine together and I study the properties, so we can say this is a high entropy alloys. And these are two publications. The first one is from Taiwan. He published in 2004. He used the element iron, cobalt, nickel, and are you listening me?
Yes, please continue.
Okay. Okay. Here is the combination. He used more than five element, iron, cobalt, chromium, copper, nickel, and different concentration of aluminium. And he studied the effect of aluminium with different element. But at the same year, another scientist, Counter, he discovered the high entropy alloys, but more than five types element he combined, and he studied many high entropy alloys. So we can say that if we combine more than five, so we can say this is high entropy alloys. How high entropy alloys is better than as compared to the conventional alloys. For example, we can tune the microstructure according to the conditions. For example, we can find a good physical mechanical properties, good thermostability, strength is good, corrosion resistance is also good. So I mean we can adjust the property according to conditions because we are working more than five elements, so we can adjust the microstructure and other properties according to conditions. But in conventional alloys, we have only two elements, for example, so we are very less option. But if we are working with more elements, we can adjust the properties. So here is a little bit difference. If we see the conventional alloys is only a one type of element, but in high entropy alloys is a different colored balls represent every different elements. So there is a more complex. If we working with more elements, then I mean the more chances of uncertainty because we are working more than five elements. So, but if we analyze the microstructure in high entropy alloys, we mostly find two types of microstructure, BCC and FCC, body center cubic and face center cubic. And sometimes we also detect the hexagonal face, but mostly the high entropy alloys show the BCC or FCC face. But first of all, we need to determine the uncertainty. First, we need to know about that, which factors can affect the high entropy alloys microstructure, maybe magnetization properties and mechanical. The first one is the combination of element. I mean, the combination of element is very important. For example, if we are working more than five elements, so the selection of element is very important role. And then the concentration of element is very important. For example, if you just change 0.2% percent concentration, your whole properties will be affected. So the concentration of element is very important. And then which technique you are using. For example, there's a lot of techniques people use, and every technique is little bit different result. And the fourth one is annealing temperature, because after preparation of sample, we anneal the sample and different temperatures, so they can change the result. And the last one is a rate of cooling. For example, you cool the sample at room temperature, in water, at outside the furnace. So all things is matter. So if we all care about all these things, then the uncertainty chance will be reduced. So the source of uncertainty, I talk about the high entropy alloy is more than 5 elements. So there is a complex composition. Therefore, the uncertainty chance is possible. And the phase stability, because when we change the concentration of element, our phase is continuously changed. FCC to BCC, sometimes hexagonal. So the phase stability sometimes show the uncertainty. And as we know, we were working more than 5. So every element have different atomic number, different atomic radius, atomic mass. So the lattice distortion effect is also possible. Then the mixing enthalpy is different. Sometimes the sample quality is different, so the possible the uncertainty. And sometimes we analyze the data, and our mistake, we detect the uncertainty. So first of all, how we can apply the Neutrosophic statics. First, we need to find where is the uncertainty, and then we decide to apply this Neutrosophic statics. This is a more accurate and flexible way to apply on and to represent your result. If your in data is uncertainty, then we can apply and we can explain result in more accurate and flexible way. Neutrosophic statics actually work on 3 elements: the truth, indeterminacy, and false. For example, this is better as compared to classical and fuzzy logic, because, for example, you have a 3 person. If one person say, today sun is shine, I ask a question, he say yes or he say no. Then the fuzzy logic say maybe say 60% yes, 40% no, and Neutrosophic say yes, 50% yes, 30% no, and 20% maybe yes, maybe no. So this is a more concise way to explain your result. There are more chances of correction. And this concept is introduced by Florentin Samardhanci. So first of all, how we approach to uncertainty and how we can apply the Neutrosophic statics. First, we find where is uncertainty. What's reason this uncertainty show? This is very important. Sometimes we find uncertainty in data, but we repeat the experiment, we remove this uncertainty. But if we repeat the experiment and we cannot remove the uncertainty, then you can apply the Neutrosophic statics and check this. When you apply the Neutrosophic statics, then you also check this is big any logic or not. Then we decide to apply this Neutrosophic statistics. For example, I explained with example in the last month I did is XRD and SAM. It's the same sample, same technique. I prepare the same conditions, means my sample in both condition is same. But when I did XRD, I find a BCC phase 73% and FCC phase in 27% in XRD result. But if we see the SAM, EBSD electron backscatter diffraction technique, I use 99% BCC phase and 1% FCC. So my sample is same, everything is same, but the different machines give different results. So this is a very big uncertainty. So what's solution behind? So there is a question, which one is correct? So I say the both are correct. But the difference, then there is a question why they give a 99% BCC and 73% BCC phase is very big difference. So the reason behind is that, for example, when I did XRD mostly we use a powder form sample. Then the every crystal is analyzed well, and then they show more deeply structure. But in SAM, we select the image. For example, I have a I have microstructure. Maybe if I analyze the area, if I analyze another area, another same means in another site, so maybe I detect more FCC phase. But this technique is take maybe 1 day. So you repeat the experiment to find a good region. So this is very difficult task, but we can. But if we try again and we not find a means close to the XRD result, then you decide to apply a Neutrosophic statics. So here is the why EBST and XRDs disagree. So this is a surface sensitive. I already explained that the EBST is a surface sensitive, but they sometimes is a very small fraction of FCC. EBST have no resolution to detect this FCC phase region, but the XRD is very sensitive to the crystallography, so they detect phase very well. But when we explain both in one, for example, in article, then how we can explain this is because there is uncertainty, so we apply the Neutrosophic statics. The Neutrosophic statics is a more flexible way here. For example, I give example. Here is in EBST we find we take pencil. In EBST, we find a 99% BCC phase, but in XRD, we 73%. Then what we will do, we we take average of both, and we explain 0.86. Similar for FCC, we take average. So this is a truth value. I mean, this is more, we can say this is a more chances to make a FCC and BCC phase. This is 100% right. But indeterminacy here is we're not much sure because there is uncertainty. So we find the difference between them, and then there is a difference is 0.26. And this is we can say maybe yes, FCC phase, maybe no, just like C. And here is falsity. If we see here is we can give a value from 0.05 to 0.10. Anyone you can, but not increase to 0.15. So we can explain the result. My screen is not moving. So the final we can say here here we say the BCC phase we can explain is in this way. For example, 86% BCC phase and 0.25 maybe FCC, maybe BCC, and 0.10 I have no much confirm. I think this is a more good way if your result is disagree to each other, you have different techniques, then you can explain in this way. My 0.14% FCC, 0.25 I have little bit not confirmed, and 0.10 is a falsity in your data is uncertainty. So we can explain, I think, is a more realistic and a flexible way to describe your result. Okay. Here is, for example, if you apply the uncertainty on one, for example, in the last slide, I applied the uncertainty on microstructure. So then you need to apply to other properties, because if you apply on microstructure, then and you also discuss about mechanical properties and magnetization. So you need to apply on this one because we are the microstructure result and your characteristics and magnetic properties we are related to each other. If your microstructure is affected, your mechanical properties also affected. So then we need to explain your results in Neutrosophic statics, other results. So here, if we see the traditional and the Neutrosophic analysis, we see here is a 50 we can see the result here. If the Neutrosophic range is higher as compared to the classical, they cover the more region. For example, for 530 to 530 to 490. So this is a more cover region. You have a more confidence interval to explain your result as compared to the traditional analysis. And this is a Gibbs free energy. If we see the classical is mostly is a one value minus 68.87 kilojoule per mole, but in Newt when I apply the Neutrosophic statistics, so I have little bit relaxation. If my structure is my microstructure, my properties change, so I can explain according to this one. I have little bit flexibility to explain the result. So this is not about high entropy alloys, but is another about a thin film in solar cell. Here I just take as example if you're how which type uncertainty income. This is a professor. My professor is from Germany. He showed this result. If you see here, there is a 18 different techniques, same sample. He used same sample, copper, indium, gallium, and silicide thin film. But when he used to detect the composition of gallium, he used different techniques, X-ray spectroscopy, Auger electron spectroscopy, and many others you see in the screen. He said that every technique give a different composition of gallium. So there is a question which technique is good, because sample is same, region is same, everything is same, but that every technique give a different concentration of gallium. So the every technique is good. Here is a question: which technique is good? It means every is good, but why they give different value? Because every technique has a different resolution they detect. Because for example, if we need a good image results, then I prefer them, for example SAM. And if you need a good composition of element, I prefer EDS. So it is depend on if you need to save a time. Some machine take 3-4 minutes to analyze data, some machine take 1 day. So this is depend on your conditions, but the problem there is a lot of uncertainty in your data, and because every technique give a different concentration of gallium. So this is only solution. If you want explain your result, you can apply the Neutrosophic statics, and you give your result in more accurate way. And the conclusion in my results, so I say the high entropy alloy is not, we can means phase to detect the phases, but also describe the fraction of phase, how much percent our phase, also the relate with microstructure, mechanical properties. Then we need to solve the problem. If in our data is uncertainty, then we apply the Neutrosophic statics. But in future, we can, in coupling with the calculation of phase diagram, is a computational software. If we apply on Neutrosophic static combination with this software, we can improve the more application. We can improvement your result and with less uncertainty. So the reference, this is my sample. For more reference, you can scan this QR code. And thank you very much for your attention.